Hello everyone. My name is Rajat Rai, and I'm from ECE fourth semester. So today I'm gonna present a presentation on energy and power spectral density and autocorrelation. So the topics we're gonna cover in this presentation are energy and power signals, energy spectral density, power spectral density, properties of PSD, filtering power signals, and modulating power signals. So we're gonna start with energy and power signals. So basically, I'm gonna give you a basic definition of energy and power signal. So energy signal is a signal that has energy only in finite time, not over all time. As we know, the power of a signal is rate of energy over time. So in the energy signal, uh, has average zero power, zero average power. So the power signal is a signal that has a finite power which is not zero, and as we can say, energy is very big, that tends to infinity. So you can see an energy signal xt has 0, less than e, but less than infinity, 0 to infinity for average energy. And power signal xt has 0, 0 to infinity for average power p, that in which time tends to infinity. So can think of average power as average energy by time. An energy signal has zero average power. Power signal has infinite average energy. Power signals are generally not integrable, so don't necessarily have a Fourier transform. We use power spectral density to categorize power signals that don't have a Fourier transform. All right. So the next presentation is energy spectral density. So energy spectral density is basically uh, describes how the energy of a signal or a time series is distributed with frequency. Here the term energy is used to generalize sense of signal processing, that is energy of a signal is. So it is defined as psi xf equals to xf whole square, measures the distribution of signal energy over frequency. Properties of energy spectral density include, we can say it's written in front of the screen, psi xf greater than equal to 0, psi minus f is equal to psi xf for xt real and xt input of the time filter with frequency response hf. The filter output xt has energy spectral density psi yf equals to modulus of hf, to psi xf. All right. So next topic, autocorrelation of energy signal. So I'm going to give you I'm just going to start with the basic definition. Autocorrelation function of an energy signal measures signal self similarity versus delay, can be used for synchronization. A signals autocorrelation and ESD are Fourier transform pairs. Power signals often do not have Fourier transform. Instead, we categorize them using power signal density. All right, so defined for real signal as you can see the formula, measures the similarity of the signal with a delayed version of itself. Autocorrelation defines signal energy E is equal to Rx 0. Since Rxt less than equal to Rx 0, can use autocorrelation for signal synchronization, as I've told you earlier. The autocorrelation is symmetrical. Rxt is equal to Rx minus of tau. It's not t, it's tau. Sorry. The autocorrelation and ESD are Fourier transform pairs. Rx tau is tends to equal to psi xf. So the next I'm going to start with power spectral density. So I'll give you the basic definition of the power spectral density. Um, a power spectral density is the measure of signal's power, content versus frequency. All right. Therefore, while the power spectrum calculates the area under the signal plot using the discrete Fourier transform, the power spectrum density assigns unit of power to each unit of frequency and thus enhances periodicities. All right. So power signals have infinite energy. Fourier transform and ESD may not exist. Power signals need alternate spectral density definition with similar properties as energy spectral density. Can obtain energy spectral density for a power signal xt that is time windowed with window size 2t. All right. Power spectral density defined as the normalized limit of the ESD for the Windows signal XTT SXF limit t tends to infinity. All right. So power spectral density measures the distribution of signal power P equal to the t tends to infinity and the formula. So and that's the power spectral density for you guys. So the next these are the properties of power spectral density. I'll explain you with the words. Um, the spectrum of a real valued process is real and even function of the frequency. All right. The spectrum of the real valued process or is real and even function of the frequency. And in the process is continuous and purely indeterministic. The autocovariance of function can be reconstructed by using the inverse Fourier transform. So these were the two properties of PSD. They were more, but and next, filtering and modulation of power signal. So let xt be the power signal with PSD SFX SF SXF. Um, if xt is input to the filter with frequency response HF, then the filter output YT has PSD SYF equals to modulation of HF 2SS 2XXF. If SXF is band limited with bandwidth B smaller than FC, so then for ZT is equal to XT cos 2 pi FCT, SZF equals to 25 SXF minus FC plus XFF plus FC. So that was filtering and modulation power signals. So I'm gonna tell you some few important points which I have written from the slides I have shown you before earlier. Sorry. So these are some important points. So the first point is energy spectral density measures signal energy distribution across frequency. Okay. The second point, autocorrelation function of an energy signal measures signal self-similarity versus delay. Can be used for synchronization. All right. Autocorrelation can be used for synchronization, basically. I've told you. Uh, a signal's autocorrelation and ESD are Fourier transform pairs. All right. You should know that by now. Uh, Power signals often do not have Fourier transform. Instead, we categorize them using PSD. Can determine the impact of filtering and modulation of power signals based on power spectral density. So these were some important points from the slides I've shown you earlier. So thank you so much. My name is Rajat Rai.